Giant students, welcome to my YouTube channel. Students, always remember, you are braver than you believe. You are stronger than you seem, and you are smarter than you think. I repeat, students, you are braver than you believe. You are much stronger than you seem, and you are smarter than you think. So students, basically, you need to believe in your own abilities. Try to love yourself. Dear students, each one of us has got some strengths and weakness. But the point is, we need to overcome our weaknesses. We need to find ways to overcome our weaknesses and strengthen our strengths. So students, with that note, let's start today's topic. Today we are going to derive two important expressions for the magnetic field at a point on the axial line and at a point on the equatorial line due to a bar magnet, which is also known as a magnetic dipole. So, in the case 1, we are supposed to find out the magnetic field due to a magnetic dipole at a point on the axial line. For that, students, let us consider a magnetic dipole. Let us consider this to be a magnetic dipole. As we have discussed, a magnetic dipole, it consists of two equal and opposite poles. Poles are the preferred regions near the endpoints of the bar magnet, where the magnetic force of attraction is maximum, right? Let us assume this to be the south pole and this to be the north pole. So, as we have discussed in the previous session, the pole strength for north pole may be represented by plus N, and for south pole will be represented by minus N. This suggests both are of equal strength but of opposite nature. This can be considered to be the center of the dipole. This is point 2. And this line is known as the axial line. It is known as the axial line. So our objective is to find out the net magnetic field due to this magnetic dipole at any arbitrary point on the axial line. So we will find out the strength of the magnetic field at point P, which lies on the axial line of this given magnetic dipole, right? Let's consider the distance of this observation point from the center of the dipole be R. And as we are aware, students, magnetic length, it's the distance between the two equal and opposite poles which constitutes a magnetic dipole. And we have represented magnetic length by 2L. Remember, it's a vector quantity directed from south to north. So, this is 2L. This is magnetic length. It is directed from south to north. Magnetic moment, it is also directed from south to north. So, this distance would be equal to L, and this distance is also equal to L. Clear, students? Total magnetic length is considered to be 2L. Therefore, the distance of the north pole from the observation point P, it would be R minus L. So it is R minus L. And students, the distance of observation point P from the south pole, obviously from the diagram it's pretty clear, it would be R plus L. This is R plus L. Okay, now let us draw the vector diagram at point P. Magnetic field, as you are aware, students, it's a vector quantity, right? From north pole, at any point outside the magnet, from north pole, the magnetic field will be directed outwards. And at any point outside the magnet, due to the south pole, the magnetic field will be directed inwards, isn't it? And students, this is the formula, isn't it? The strength of the magnetic field due to a source pole, it's given by mu naught M divided by 4 pi R square. This is the basic formula. R is the distance of the observation point from the source pole under consideration. Right? Okay. This is the basic formula which we'll be making use of. Now, due to this north pole, the magnetic field at point P, would be in magnitude given by, suppose Bn. It would be given by mu naught over 4 pi. Magnitude, the strength of the pole is m, and the distance of the observation point from the north pole is r minus l. So make use of that formula. So we get r minus l whole square. And it will be directed outwards, right? So what about the strength of the magnetic field at point P due to the south pole? Due to the south pole. The formula is mu naught divided by 4 pi. Pole strength, its magnitude, it is again smaller. And distance of the observation point from the south pole, that would be r plus l, isn't it? So it will be r plus l. Clear, students? Now observe these two. Obviously, the observation point being closer to the north pole, the strength of the magnetic field at point P due to the north pole would be much larger as compared to the magnitude of the magnetic field at point P due to the south pole, isn't it? You can easily check. Numerator for both the cases is same. Here denominator is large, therefore Bs is less than Bn. So Bs is less than Bn. Right? Now let's represent it diagrammatically at point P. Let's draw the vector diagram. So north pole, due to this, the magnetic field at point P will be directed outwards, like this, away. This is Bn. Now, due to the south pole at this point, the magnetic field will be directed towards the south pole. So it will be like this. This is Bs. And for Bs, the length of the arrow is smaller as compared to the length of the arrow representing Bn. It is because of this reason. Bs is less than Bn. So students, what's the angle between these two? They are oppositely directed. The angle between them is 180 degree. So, resultant of two vectors when they are oppositely directed is difference in the magnitude of the two vectors along the direction of the dominating vector. So what will be the result over here? So B axial, it would be Bn minus Bs. Why minus sign? Because the angle between these two is 180 degree. And what will be the direction? Along the direction of the dominating one. Bn is dominating one. So its direction would be like this. So students, simply with the help of this diagram, we are safely able to conclude that the direction of B axial is from south to north. That is along the direction of magnetic moment. That is along the direction of magnetic length. So this we have done. B axial is along the direction from south to north, that is towards right in this case, from south to north, that is along the direction of m vector, magnetic moment or magnetic length. Magnetic moment or magnetic length, both are directed from south to north. So this is a very, very important point. So at any point on the axial line, the direction of the magnetic field will be always along the direction of the magnetic moment. It will be always along the direction of the magnetic length, that is from south pole to north pole. Clear, students? So that's the direction of B axial. Now let's find out the magnitude of B axial. Okay, B axial. As we have stated, it's Bn minus Bs. Let's substitute the value. So mu naught m divided by 4 pi r minus l whole square minus Bs. Substitute this value of Bs. It is mu naught m divided by 4 pi r plus l whole square, isn't it? So you can take this as common. Mu naught m divided by 4 pi. This can be taken as common. So what will be left with is 1 divided by r minus l whole square divided by 1 divided by r plus l whole square. Right? Now it can be easily solved. So it will be mu naught small m. It's the pole strength small m. So let's take the LCM. It is in the form of a minus b whole square, a plus b whole square. It will be equal to a square minus b square whole square. So it will be r square minus L square whole square, right? And over here it will be R plus L whole square minus R minus L whole square. Clear, students? Now I hope this can be easily evaluated. It's in the form of A plus B whole square. So that will give us R square plus L square plus 2RL minus, inside bracket, it is in the form of A minus B whole square. So it will be R square plus L square minus 2RL. So it's inside bracket and outside it's negative sign. So R square minus R square get cancelled, L square minus L square get cancelled, 2RL minus plus 2RL. So in the numerator we will be left with 4RL. Students, I am very sure you can easily solve this numerator part, isn't it? So we will obtain B axial is equal to mu naught m, it will be 4RL divided by 4 pi R square minus L square whole square. Clear? Now, in case I want to represent the result in terms of the magnetic moment of the dipole, then we are aware, students, magnetic moment, it's given by product of magnitude of either of the pole strength and the distance between them. Isn't it? This is magnetic moment. So, M multiplied by 2L, that will give us magnetic moment. So, what we get is 2 will be left twice mu naught mr divided by 4 pi r square minus L square whole square. So students, this is the expression for the magnetic field at a point on the axial line due to a magnetic dipole, right? Capital M over here is the magnetic moment which is directed from south to north. B axial is also directed from south to north, that is along the direction of M vector or along the direction of 2L vector. So this is it. I hope you have understood this article. Now before proceeding further, we need to discuss a special case. And the special case is about a short dipole. When we say the dipole is short, when the distance of this observation point from the center of the dipole is very large as compared to the dimensions of the dipole, right? So what we'll do is, let's consider the special case over here for a short dipole. That is when R is very large as compared to L. Just imagine, point P is lying at a very far away distance from the center of the dipole. So R is very large as compared to the L, which may be considered to be the dimensions of the dipole. So in such a case, the dipole may be considered to be a short dipole. So when R is very large as compared to L, then the higher powers of L, it will be still smaller and hence can be neglected in comparison to the higher powers of R. So therefore students, logically, R square minus L square, it can be approximately written as R square. So L being very small, L square would be still smaller and hence can be neglected as compared to R square. Therefore, B axial, it will be equal to twice mu naught mr divided by 4 pi r square minus L square can be written as only r square to the power square. It will give us r to the power 4. Therefore, B axial, it's equal to twice mu naught capital M divided by 4 pi r cube. So this is the formula which is to be used in case the magnetic dipole under consideration is short. That is, this condition is fulfilled. Then only this condition or this expression can be used. One thing to be noted is that for a single isolated hypothetical pole, the magnetic field varies inversely as the square of the distance of the observation point. But for a magnetic dipole, the magnetic field at any point on the axial line, it varies inversely as the Q of the distance of the observation point from the center of the dipole. So for a magnetic dipole, magnetic field varies with distance r as 1 by r cube. Clear, students? So we are over with the first article, that is the expression for the magnetic field at a point on the axial line, its expression, direction, and we have discussed the special case as well, right? So students, let's proceed with the second article, which is the equatorial line. So as you are aware, equatorial line is basically the right perpendicular bisector. So a right perpendicular bisector of the magnetic dipole that will act as an equatorial line. So again, in this article we are supposed to find out the expression for the magnetic field, as well as we will discuss its direction along with the special case, that is for the short dipole. So let me draw the diagram over you. This is the dipole. We have considered this to be the south pole, and let us consider this to be the north pole. This is the center of the dipole. This is O is the center of the dipole, and this is L, this is also L. So magnetic length we have considered to be 2L. It's a vector quantity directed from south to north. This is the direction of magnetic length or magnetic moment, right? So this is the center. Now draw a right perpendicular bisector. It will divide into two equal parts, and this being 90 degrees. So it will act as right perpendicular bisector. So this line, students, will act as equatorial line. This line is known as the equatorial line, right? Now our objective is to find out the magnetic field at a point on the equatorial line. So as was in the earlier article, we have considered the distance of this observation point from the center of the dipole as r, right? So the distance of this observation point from the north pole, we can make use of Pythagoras theorem. So it will be r square plus L square and square root of this. Similarly, the distance of the observation point P from the south pole, it will be exactly same, this being perpendicular and this being base. So it will be again r square plus L square and square root of this. Clear, students? Okay. So these two are equal. Now let's consider the magnitude of the magnetic field at point P due to the north and the south pole. Now look, at this point it is equidistant from both the north and the south pole. Its pole strength is plus m, its pole strength is minus m. So this point P being equidistant from south and north pole, the magnitude of magnetic field at point P due to the north pole must be equal to the magnitude of the magnetic field at point P due to the south pole. Let us consider it to be B, C, and it will be equal to mu naught m, strength of the pole strength and magnitude is m 4 pi r square. What is r? It is the distance of the observation point from the pole. So it is r square plus L square and square root of this. So square of this. So the square root gets eliminated. So we will be left with r square plus L square. Square root of r square plus L square to the power square. So we will be left with this only. Clear? Now let's draw the vector diagram at point P. Because students, you are aware, whenever we deal with vector quantities, it has to be dealt using laws of vector addition by drawing appropriate vector diagram. Now due to this north pole, the direction of the magnetic field at point P will be in the outward direction like this. This is Bn. Clear, students? It's in the outward direction. At point P, the strength of the magnetic field, or rather the direction of the magnetic field due to the south pole will be towards the south pole. So it will be like this. It is like this. So this is Bs. This is the magnetic field due to the south pole. Also students, these two sides are equal. We are aware the angles opposite to the equal sides of a triangle are equal. Therefore, if these two sides are equal, therefore these two angles must also be equal. If this is theta, this will be also theta. Right, students? So, using exterior angle theorem, this angle, this is the exterior angle, and theta plus theta, that is 2 theta, it will be sum of the two opposite interior angles. So, it will become 2 theta. Clear, students? So, here what we have used is, the exterior angle is equal to the sum of the opposite interior angles. Now again, we will make use of the very basics of vector algebra. These are the two vectors which are of equal magnitude. Now we are aware, students, whenever the two vectors are of equal magnitude, then their resultant bisects the angle between them. So, if these are the two adjacent sides of a parallelogram, then the resultant at the point will be given by the diagonal of the parallelogram. And in this case, since both are of equal magnitude, therefore, the resultant will bisect the angle between them. Therefore, this is the resultant. This is B equatorial. And it will bisect, means this angle will be theta and this angle will be theta. Now, since this is theta and this is also theta, but they are forming pair of alternate interior angles, therefore, these two must be anti-parallel. These two must be anti-parallel. So, what do you conclude, students? With the help of vector diagram, we are able to prove that at any point on the equatorial line, the direction of the magnetic field is from north to south. It is from north to south. That is in a direction opposite to that of magnetic moment or the magnetic length. Remember, students, in the case of axial, the direction of the magnetic field is along the direction of magnetic moment or magnetic length, that is from south to north. But here, in the case of equatorial line, the magnetic field at a point due to the dipole is from north to south, that is in a direction opposite to that of the magnetic moment or magnetic length. So, B equatorial is directed from north to south, that is in a direction opposite to M vector or 2L vector. So do remember this. So B equatorial is always opposite to the direction of M vector and 2L vector. So what will be the angle between B equatorial and M vector? It should be 180 degree. What is the angle between B axial and M vector? It will be 0 degree, right? Okay. Once we have obtained the direction, now let's concentrate on the magnitude part. Let's find out the magnitude. We are aware, students, if the two vectors A and B are inclined at an angle theta, then the magnitude of the resultant is given by square root of A square plus B square plus twice AB cos theta, isn't it? So over here, both the vectors B and Bs each are of magnitude B. So it will be A square plus B square plus twice AB, BB, that will become B square. Cosine of the angle between these two. What's the angle between these two? It's 2 theta. Right? So, it will be 2b square can be taken as common. So, it is 1 plus cos 2 theta. Still further, we can write it like this. 1 plus cos 2 theta is 2 cos square theta minus 1. Plus 1 minus 1 get cancelled. So, we are left with 2, 2. That is 4 b square cos square theta. Which in turn will give us twice. Students, which in turn will give us twice b cos theta. Right? This is the magnitude. Now let's substitute the value of b and cos theta. We will get the expression. Okay. Therefore, b equatorial, it is equal to twice. Substitute this value of b. It is mu naught m divided by 4 pi r square plus l square multiplied by cos theta. Now students, it's a right angled triangle. So cos theta would be base over hypotenuse. So base is L. Hypotenuse is square root of r square plus L square. Clear students? Now look, m into 2L. As you are aware, the magnetic moment of a magnetic dipole is m multiplied by 2L. This is the pole strength and this is the magnetic length. So this we are already aware. So in order to express this expression in terms of magnetic moment, substitute 2mL with capital M. It is the magnetic moment divided by 4 pi r square plus L square to the power 3 by 2. Students, this is the expression for the magnitude of the magnetic field at a point on the equatorial line. Clear students? Okay students, now let's discuss the special case. Special case is for a short dipole. That is, when the distance of this observation point from the center of the dipole is very large as compared to the dimensions of the dipole. That is, mathematically we are dealing with the case when r is very large as compared to L. As I stated students, since L is very small, therefore higher powers of L would be still smaller and hence can be neglected when compared to the higher powers of R. Therefore students, R square plus L square, it may be written as R square. Now what was the expression for B equatorial? Let me write it over here. It is mu naught M. M is the magnetic moment, which is M into 2L, right? 4 pi r square plus L square to the power 3 by 2. This was the expression for B equatorial. Now for a short dipole, this assumption is to be used. So in place of r square plus L square, we can write r square. Therefore, for a short dipole, B equatorial, it will be equal to mu naught M divided by 4 pi r square plus L square can be written as only r square to the power 3 by 2. So that will give us mu naught M divided by 4 pi r. Clear students? Here again you can see the magnetic field at a point on the equatorial line varies with the distance r as 1 by r cube. So this is a very important point to be noted down. And direction, as we have discussed students, it is in a direction opposite to that of magnetic moment. That is, it is directed from north pole to south pole. Clear? So we are over with this article as well, along with the special cases. Now before we conclude this session, let us recap the entire expressions of the entire topics which we have discussed during this entire session, right? So let me write down the formulas and the important points which we have discussed for the last 30 minutes. Okay. For axial, what was the formula, students? B axial is equal to mu naught, isn't it? Twice M divided by 4 pi r square minus L square whole square. So this was the expression for B axial, isn't it? And direction, that is very important. So it is directed from south to north. That is along the direction of magnetic moment or along the direction of magnetic length, which are also directed from south to north. Now for a short dipole, B axial, it is equal to twice mu naught m divided by 4 pi fact here it should be r, like this. So for a short dipole, L square can be neglected. So r square to the power square, it will become r4. R divided by r4, it will become r cube. So this is the expression for the B axial at any point on the axial line due to a magnetic dipole, and this is the formula to be used when the dipole under consideration is short, right? Okay. Second, for equatorial, B equatorial, just now we have discussed, it is mu naught m divided by 4 pi r square plus L square to the power 3 by 2, isn't it? And its direction is opposite to that of the magnetic moment, opposite to that of magnetic length. That is, it is directed from north to south. Always remember it. And for a short dipole, B equatorial, it is equal to mu naught m divided by 4 pi. L square will be neglected, r square to the power 3 by 2 will be left with r cube. Right, students? So, consider these two. So, common point is magnetic field at a point due to a magnetic dipole varies with distance r as B is inversely proportional to r cube. Clear, students? One more very important point. For a short dipole, B axial divided by B equatorial. Let us consider this to be 1 and let us consider this to be 2. So 1 divided by 2. So B axial divided by B equatorial. Mu naught m over 4 pi r cube is common. So we will be left with 2 is to 1. So this is also a very important relationship. It's actually same. The result is actually same as was obtained in the case of electrostatics when we discussed the topic of E equatorial and E axial, the electric field at a point on the axial and equatorial line due to an electric dipole. There also we have obtained the same result, right? So B axial for a short dipole is equal to twice B equatorial. So students, we have covered each and every topic, right? Axial and equatorial. So I hope you have understood the things which I have tried to convey to you. So that's it for this particular session. Then do join me in my next lecture then. Thank you.